I'm Yuji.
Today we would like to present the theory that GNI is in AM2. First, I will review the concept used in the proof. The first is the IP. IP is that for every integer k that is greater or equal to 1, we say that a language error is in IP k if there is a probabilistic polytime Turing machine V that can have a k-round interaction proof with a function p such that if x is in error, we can have that if there exists a p such that the probability of the outcome of V with Vp as the interaction is equal to 1, the probability is greater than 2 over 3. And if x is not in error, we can have that for all p, the probability of the outcome of V with Vp is equal to 1, the probability is smaller or equal to 1 over 3. And the class AM is that for every k, the complexity class AMK is defined as the subset of IPK, and that we restrict the verifier's message to random bits, and the verifier use no other random bits except for the random bits in the verifier message. And now here we come to the concept of GI and GNI. GI is a problem that given two graphs G1 and G2, we would like to decide whether G1 and G2 are isomorphic. And of course, G1 is in NP, as we can use the description of the permutation from G1 to G2 as a certificate. And we have that GNI is in NIP1, that is a one. We can have a one-round interaction proof that to have G1 and G2 are not isomorphic. And the proof code is as follows: when the verifier given G1 and G2, and it randomly chooses a random variable I from 1 or 2, and it constructs a new graph that is a random permutation of GI, and it sends the graph H to the prover, and the prover will decide whether H is constructed from G1 or G2. If I is equal to j, the verifier will output non-isomorphic. And if I is not equal to j, and the verifier will reject. And if we use the parallel and parallels this interactive proof, and because the channel bound, we can get this, and this language can be defined in a one-round interaction proof. And here comes the trick we use in the proof. That is the pointwise independent hash function. Every x1, x and x prime that is in 0, 1 to n, and x is not equal to x prime, and y prime is in 0, 1 to k, and the probability over hx is equal to y, and hx prime is equal to y prime is equal to 1 over 2 to 2k. And this is equivalent to if we randomly choose an h from h, the big H set, we can, for the two random variables y and y prime, we can have this, the hx and hx prime is uniformly distributed over this exist such functions that can be efficiently computable, that we can define HAB, that is a set of functions HAB that is maps of x to ax plus b, and this big H can be efficiently computed, and we can satisfy the following conditions.
Now we have already shown everything we need to do the proof, and here we do the proof now. First, we define a set S, which is a tuple of H pi, and H is a graph isomorphic to G1 or G2, and pi is the automorphism of H. Basically, we some kind of only need H here. So if G1 is not isomorphic to G2, then S should have a size of 2n factorial. So since G1 or G2 may have less than n factorial equivalent graphs, so in that specific H, it will have a non-trivial automorphism. We add pi here to only make sure that S has a size of exactly 2n factorial. So if G1 and G2 are isomorphic, then it would have a size of n factorial. And here we show a very simple verification process. Let k be 2n factorial, and it is in between of some 2 to the power of k minus 1 and 2 to the power of k minus 2. This is small k. And S is in this length 0, 1 string, and M is big enough to encode all S. And here is a one-round verification process. First, the verifier randomly choose a pairwise independent hash function from M to K, and randomly select a Y in length K, and send these two things to the prover. And the prover, as an all-power machine, can easily find if there is an X in S, such as H, this H, X is equal to Y. If there exists such as, it can find it, and if there is not, then it can do nothing. And the prover send this X back to the verifier, and if such as does not exist, it can just randomly send anything else. And when the verifier receives the X, it checks whether HX is equal to Y and X is in S. And if these two things true, then it accepts, otherwise it rejects. And this verification process is basically based on the intuition that if the size of S is big, then this thing would happen with a big probability. Otherwise, the probability of this happens is pretty small. Note that only this verification process here is not enough to prove that GNI is in AM2, since this process, the verifier would be wrong with a pretty high probability. And now we show that only change a small number of things here, we can make this verification process very powerful. And we define this probability, which here to be Q, and this is H in a random pairwise independent hash function, and Y is a random string, and this happens, which is Q. This Q is actually the probability of this thing happen. So for S, which has a size between these two numbers and the small k here, we define P. P is the size of S over 2 to the k. And we'll show that no matter S is equal to 2n factorial or n factorial, as long as this formula hold, and we define this P, and this formula will hold. And we can easily see that if S, the small k here for the S equals 2n factorial is actually bigger than the one for S equal to n factorial. And now we show this this inequality is true. This part for Q is smaller than P, is almost trivial, since for every X in S, this happens with a probability of 2k, 1 over 2k, since this is a random distribution here, and so for every X in S, hx equals to y happens with the probability of. So since S only has at most S has the size of S of elements, so the probability of Q happens is at the most this number times this number, which is P. So for the other side, we write Q in another way. According to the inclusion-exclusion principle, we can write Q as the sum of x in S and the probability and minus the sum of x not equals to x prime and in S and this thing and many things else. And actually Q is larger than or equal to only the first two sums here. And the proofs can be found in the appendix of the textbook. And here we only show the basic intuition for this, why this inequality holds. And basically, if, for example, if we have 3 cycles, and Q is the probability of the area for the 3 cycles, and this thing is just the sum of these areas add together, and we minus all the 3 intersections, and actually we minus these 3 things, and we actually minus this thing more than 1 times, which is actually more than 2 times. So this will make the whole probability smaller than the exact one. So Q is bigger than or equal to this thing. And also, as I mentioned before, if you want to see the exact proof, you can find it in the appendix of the textbook. And since Q is larger than or equal to this thing minus this thing, and this one obviously is exactly the same as the previous one, is equal to. And this thing, since according to the definition of the pairwise independent hash function, we can find that the probability of this thing happens is we randomly choose 2 things from S times the probability of both of these things happens. This is S size square. So we simplify this formula, we can get this number, and this is P. This is P. And this thing, since S has in this range, so this number is actually smaller than 1/4. So the whole thing is actually bigger than 3/4 times P. This is 3/4 and this is P. So we have finished the proof for 3/4 P is smaller than Q. And now we show that how this formula will help to prove that G and I is in AM2. Assume that big K is 2n factorial, and we define 2 to the small k minus 2 is smaller than k, is smaller than k minus 1. This is big K, this is small k. And if this is true, then if S has a size of 2n factorial, then according to what we proved before, then this thing will happen. Actually, this thing will happen with a probability of in this range. And if the size of x is equal to n factorial without 2 here, then for that s, this small k is 1 less than the small k for the s equals 2n factorial. So also according to this, for that q, it will happen within in the probability range 3/8 times p. So as we can see, for example, this is 0 and this is p. If s has a size of 2n factorial, then the q will happen with a probability of 3/4p and p, which is in this range. And if the size of s is n factorial, it will happen in 3/8p and 1/2p, which is in this range. So as we can clearly see, these two ranges are well separated. So we can set a threshold here, which is 5/8p, which is half of this plus this. So even if we only have one round of verification, but we can select many random and independent y and send them all together to p and let p to give us x for each y. And if more than 5/8 of the total number of y's, this thing happens, then the verifier accepts, otherwise it rejects. According to the Chernoff bound, according to the Chernoff bound, we only need a constant number of y to make the probability of verifier to be correct is bigger than or equal to 2/3, and yes. So we only need constant number of y's to make the verifier correct in the range we need, which is in AM2.